Kevin Gurney is an atmospheric scientist, ecologist, and policy expert, currently working in the areas of carbon cycle science, climate science, and climate science policy at Northern Arizona University, where he is a professor in the School of Informatics, Computing, and Cyber Systems. He has degrees from UC Berkeley, MIT, and Colorado State University. His current research involves simulating global carbon cycle using what's called an inverse approach, meaning linkages between terrestrial carbon exchange and climate variability and deforestation and carbon climate feedbacks. I suspect tonight he'll be talking about his fossil fuel CO2 simulations at FFDAS, the National Vulcan and Urban Hestia scales. Dr. Gurney is an IPCC lead author, an NSF Career Award recipient, Sigma Chi Young Scientist recipient, a Fulbright scholar, and he has published over 150 peer-reviewed scientific articles with multiple papers in Nature and Science, and of course, a book from MIT Press called Mending the Ozone Hole. So with that, Dr. Gurney, I'm going to allow you to share your screen, and you can start.
Okay, great. Thank you, Aaron and Adam, for hosting, and welcome to everybody online. You should be able to see my presentation. I'll go into presentation mode. So as long as that looks okay, we'll get going. So the outline of my talk, I'm going to have a few things we'll touch on. First, I want to set some context on climate change. Most of you listening know what climate change is, and you know plenty of things probably about it, but I'd like to just set some quick context, bring us up to date with the latest information on what's happening with climate change. And then from there, go into the core of the data part of this story that I want to tell about greenhouse gas emissions data, and what we're doing to try to deliver a little more relevant data and information to the policy world. And then finally, some next steps and larger visions of where this work is going. I'm going to be talking mostly about the work that I do in my research group, but I work with lots of colleagues doing similar work around the planet. But I'll be telling this mostly from the work that I do at NAU. So the first important piece of context is where we're at in terms of temperature rise around the planet. This is from the very recently released IPCC AR6 report. And on the left, this is a bit of a busy graph, I understand, but on the left, you're seeing the temperature trend. The modern temperature record is sort of the black line on the very right-hand side. I think I have a cursor here. Right here is the measured temperature record. Prior to that is the temperature record that's reconstructed from indirect data, ice cores, pollen records, other things have been put together to try to reconstruct temperature in the past. And as you can see, we effectively in the 20th century have entered extremely unprecedented temperature rise. We're now warmer than any time over the last 650,000 years. Again, most of this in that 1850 to present time period. On the right, this graph shows both, again, that observed temperature record. Now we're just looking from 1850 to the present. That little piece over here is now blown up into this graph. And that same black line is the black line over here. But along with that are what climate models predict or project for temperature rise. And importantly, this shows that when you take a climate model and you put in only natural variability, things like the variation in solar output or volcanic eruptions, no greenhouse gas emissions, this green line is what the models tend to simulate. Relatively flat, but it's got lots of variability. And climate always has that type of natural background variability. But when greenhouse gas forcers are put into these models, they tend to reproduce the past temperature record pretty well. And indeed, in the last 20 years, this has got increasingly better and better, and the climate models are starting to perform very, very well. And the reason this is important is it gives us a bit of confidence on what these models say in the future. So the takeaway messages here is temperature rise is unprecedented, and that climate models are performing so well that we're trusting them more and more on what they're going to tell us about the future. This is, again, I'm sorry, a busy, very busy graph, and I'll sort of digest it for you. This is sort of then what are some of the things that we're seeing associated with that temperature rise. And it's just a sample because there are many, many things that are now being observed all around the planet associated with the climate system that appear to be a manifestation of this broad temperature rise. And up here in the top, this is attempting to sort of be a map of the world. This is North America here, South America here, Europe and Eurasia all across here, Africa, Australia, etc. But the top plot are instances of hot extremes. And what this is saying is that essentially everywhere almost on the planet, we are seeing unprecedented hot events. These are events that normally would occur very infrequently, maybe once every 50, 100, or even 500 years. We're starting to see them back to back within a few years of each other. So these extremes are increasing. This here is heavy precipitation. Same story, not as dramatic, but lots of extreme events occurring all across the planet. And then finally down at the bottom is agricultural and ecological drought. Again, not as dramatic as temperature. Takes a little while for that signal to get through systems like this. But again, all still on the sort of positive extreme side of the ledger, where more and more of these extreme drought and agricultural stressors are occurring. So takeaway here, extremes are increasing and the link to anthropogenic climate change is becoming clearer and clearer. Now, so what does this mean for the future? And this shows, this again is that same black line that I've showed in the previous plots of the temperature record observed from 1950 now to the present. And it looks a little more compressed, and that's because now we've added on projections into the future. And because they span such an enormous temperature range, that past 1 degree, 1.2 degree temperature rise looks much smaller. And this sort of says that in some ways, though the past is concerning and we've seen a lot of temperature rise, it's what's going to happen in the next 50 to 100 years that really is worrisome. And the other important point out of this plot from these projections is that all of this envelope, or most of this envelope, is really a choice. It's about how we grow, what type of energy systems we rely on or continue to rely on. We have a lot of power to change or choose amongst these futures that are exhibited here that the climate models will project depending on how much, let's say, fossil fuel energy you put into the system, how much population growth you put into the system, how much income growth or GDP growth you put in. All of those types of variables are mixed together to try to project what can happen in the future. But let's just look at the 4 degree mark. It's not at the upper end of this extreme, nor is it at the lowest, but unfortunately, it's looking like the most likely or increasingly likely part of this envelope that we're going to be in unless we change things pretty rapidly. And if you look at that 4 degree temperature mark and you look at what climate models project, here are just 3 of the many things they project for the future associated with that temperature rise. Here, of course, is temperature right here, more extreme at the poles, less extreme typically at the equator. Lots of reasons for that. I won't go into that. Here's precipitation showing drying over certain portions of the planet. For example, in the area that I live in the Southwest, looks like the future is going to be a lot drier, not great for this part of the world. Some places become much wetter. The Amazon forest becomes much drier. A lot of the projections show that shifting from a forest system over to a predominantly grassland type system, and so on and so forth. A lot of changes in the future associated with precipitation. This is probably even more important part of hydrology, which is projections of soil moisture in the future. And soil moisture is critical for non-irrigated agriculture all around the planet, which is the majority of agriculture. And again, much of the interior of the United States becomes much drier, places where we grow an awful lot of food. In addition to Europe, all through the Middle East, and of course, the very dramatic decline in soil moisture in the Amazon tropical forest region in South America. So what's causing this temperature increase? As again, most people know, it is the concentrations of a few key gases in the Earth's atmosphere, carbon dioxide being the primary driver, but there are many, many greenhouse gases. Methane's typically number 2, nitrous oxide is number 3, and there are many others that are less in terms of magnitude, but important when you put them all together. There are also agents that we're emitting into the Earth's atmosphere that actually have the opposite effect on climate, for example, sulfate aerosols. So this mixture of all these different gases we're emitting is really what's underneath that temperature rise. Now, what's causing the rise in CO2? The predominant greenhouse gas in the atmosphere is the combustion of fossil fuels. And this shows just the amount of energy derived from fuel, including biomass and nuclear and hydro, from 1850 up till almost the present. And again, not a big surprise here. We used to be a biomass-centered energy system a long time ago, but now we've increasingly shifted to a fossil-based energy system. And it's the combustion of fossil fuels that gives rise to CO2 emissions, which is the primary driver of climate change. So now I want to talk about getting a little deeper into the data associated with greenhouse gases. Now, I said climate data in this talk, but I'm really going to focus, because that's a very large arena of data. I'm going to focus mainly on greenhouse gas emissions data. And I'm going to talk about CO2 and greenhouse gases interchangeably, just because CO2 is the dominant gas. But as I said, there are others, but we often use CO2 as just sort of the common language to describe all greenhouse gases often. Now, aside from that sort of bulk emissions, starting in, let's say, the late 1980s, early 1990s, the magnitude of the problem was becoming recognized, and the UN and international activity began to organize around doing something about it. And the first thing that's done is to try to then figure out where on the planet are the emissions occurring, who's effectively responsible, and therefore how can we construct some sort of policy regime to do something about that. This occurred under the umbrella of something that's, the acronym is the UNFCCC. This is the United Nations Framework Convention on Climate Change. And it's a convention which essentially means that all the nation states on the planet get together and recognize a problem and the magnitude of a problem. And then out of that convention, which is a treaty, will come specific protocols about what specifically is going to be done through a sort of loose regulatory mechanism to do something about the problem. In this case, reduce emissions of greenhouse gases. And so all nation states started making what are referred to as these inventories, or just a counting up of what their emissions are. It's nothing more than a table of, you know, how much CO2 is coming from this sector, how much CO2 is coming from that fuel, et cetera, to try to get a national account of emissions. But very quickly, probably starting then about in the late 1990s, it was clear that a lot more information was going to be needed. And there were a variety of forces that were at play that were pushing towards better and more detailed, more elaborate information. And it came really from two general categories. On the one hand, decision makers, policy makers at multiple scales, there was a rapid increase in the amount of information they needed to make reliable, prudent decisions about what to do. And similarly, within the scientific community, we were doing all sorts of things to understand CO2 and other greenhouse gases as they move around the planet, as they move in and out of the oceans, out of the terrestrial biosphere. And so there was a lot of new science emerging. And these two forces, I think, set the stage for what I'm going to argue is kind of a new data science around greenhouse gas emissions. So the first force that came out of the decision-making or policy world really, again, was associated with that international negotiating process. And I've put 3 photographs up here that kind of bookmark some of those meetings, because the countries of the world meet once a year in a very formal way. It's going to happen this November, the 27th of these conference of parties or meetings of all the nation states of the world. And the top left picture is actually from Kyoto in 1997. The middle picture is from Bonn, Germany in the year 2000. And then in 2010 is the picture on the bottom from Copenhagen. I took all three of these pictures, and the reason I put them up is they're interesting anecdotes about what climate can do. In the top photograph in Kyoto, this was an exhibit that I think I can't remember which environmental group put up, of these frozen penguins. And the idea is every day when all the negotiators would come into the negotiating hall, the penguins would slowly melt. But of course, as luck would happen, it was an extremely cold November in Japan that year, and the penguins refused to melt, which was somewhat frustrating. And then in the middle picture in Bonn, Germany, this year, another ice sculpture was made of the planet. And indeed, that did melt. And in this case, kind of maybe luckily or unluckily, the side that represented the United States was the part that sort of caved in the first. And then Copenhagen was an important bookmark that I'm going to talk about in a minute. That negotiating process, the first big force that started to emerge from it, is the fact that even though nation states were making these accounts as the regulatory reality, as a protocol, let's say targets that might have consequences began to emerge, it was clear there needed to be some form of verification of these emission accounts. And it's represented by this particular National Academy report that was written in 2010 that really started to outline, hey, scientific community, we're going to need a lot more capacity to be able to actually independently verify what countries are reporting. Very sensitive topic internationally, because many countries are not often happy with the idea of independent bodies verifying something that occurs within their domestic economies. But nonetheless, it was recognized as a critical need. The next sort of policy force that came out of not just the international process, but an emerging subnational process was the rise of cities, of states, provinces that began to voluntarily take on targets themselves. You've probably heard of lots of cities taking on targets that sometimes align with the international regime, sometimes are very independent of it. And that all was important within the context of the fact that when you look at emissions around the planet, cities, where everybody lives, accounts for 2/3 to 3/4 of all the emissions on the planet. So not only was it important that these new players were coming into the international sort of policymaking regime, but they were important players. And also, urbanization is a rising and rapid trend. We tipped over 50% in sort of the 2010s, and now urban areas around the planet are expected to triple by 2030. Urbanization process as a rate is going to double by 2050. We're effectively becoming an urban planet increasingly. So cities and these places where people live are important elements in this larger negotiating context, and they placed additional needs on the data information needed to track greenhouse gases. The third force that I'm going to mention is financing. And this came about because as, again, the policymaking process got steam, it was clear that markets were probably going to be an important part of this. And indeed, I would argue they're a critical part, just because, as we've seen, pure altruism will unfortunately not solve this problem. We're either going to have regulation, and even if we have regulation, we're going to need significant investment to do the mitigation that's needed. And that investment has to be part of some sort of market. It's hard to get investors and people into mitigating without some sort of financial market mechanism to make it go. Now, this stuff has emerged voluntarily. You may have heard of carbon credits, where you set aside a piece of forest, and then that credit can be used to obviate some emission rise or some steady emissions from an industrial source. The voluntary markets have occurred around the planet. There's trading going on. It's still very weak, but it occurs. And indeed, it's so much that there is indeed a price on carbon within a couple of these nascent kind of markets. But I would argue, even though that's exciting and there's been an emergence of this market, it's still far, far too small to make a difference. this needs to scale up in substantial ways. And one of the reasons it hasn't scaled up is that the currency, the greenhouse gas emissions data itself, is simply not trusted. It just hasn't been quantified as well as these markets need it to be. I often say to people, nobody buys a stock that's $1 plus or minus $10. You need to know that what you're investing in is worth exactly what is said. And so that's another force that emerged. Now, there are a couple within the scientific community that also created pressure to do better on greenhouse gas data. The first was the fact that the scientific community was increasingly measuring CO2 in the atmosphere in denser ways all across the planet. This is the sort of ground and aircraft network of measurements for CO2 and in some ways methane as well, all around the planet. It started out with 2 stations in the 1950s, and now it's coming into 150 stations around the planet measuring CO2. And that gives you a lot more detail, just alone having those measurements. Now, similarly, we now have launched satellites in space that measure CO2 from remote platforms. Probably the best known of these is the Orbiting Carbon Observatory, or OCO. Its first launch in 2009, I think I have that right, failed. It actually crashed into the Pacific Ocean. Normally, when you lose a satellite as part of a larger mission, that's the end of the line, you're cut out. But in this case, because it was such a national priority, the mission team got a second satellite, and indeed now there's a third flying in space. So there's 2 up there that measure, at least in this mission system, measuring CO2 from space. And of course, they're doing so in very fine blocks along these tracks from the remote platform, which again gives more detail, more spatial detail, more temporal detail on emissions, and sets up a lot of new potential science that might be helpful in the policymaking world. And it's important to measure CO2 in detail because really, when you look at CO2 in the atmosphere, this is what it looks like. It is not just one number everywhere. That is it. The bulk of the background is one number, but on top of that is an awful lot of detail. And in this case, it looks just like weather. And that's because CO2 is non-reactive. Most of the greenhouse gases are non-reactive. In fact, that's a key ingredient of becoming a greenhouse gas, is that you don't disappear, but stay around in the atmosphere. And so CO2 just gets moved around with weather. But this picture also has a couple of interesting attributes associated with it that you can see immediately. First of all, the northern hemisphere has far, far more CO2, anthropogenic CO2, than the southern hemisphere. And that's because that's where the majority of industrial activity occurs. That's where the majority of the emissions are. Similarly, as you look in the north going sort of across longitude lines, you see 3 big bullseyes. And those are really the main bullseyes of industrial activity on the planet. That's shifting, of course, over time, but you see the big North American sort of East Coast, Central, Eastern US industrial belt. You see all the industrial activity in Western Europe, and then industrial activity increasingly in Asia, China, and sort of Central Eastern Asia. So it's a very indicative map, but it shows why the detail is so very important. So all of these forces, I would argue, combined to create a demand for a new data science. And so between the policy needs and the emerging scientific capabilities, this new approach and new systems to deliver this information have emerged. And that's where I've focused a lot of my research in the last 15, 20 years. And the first one I'm going to show is a global system that we have called FFDAS, which stands for Fossil Fuel Data Assimilation System, a bit of a cumbersome phrase, but we attempt here to quantify CO2 emissions across the entire planet every hour at about 1 kilometer spatial scale over multiple years. Now, we don't have a lot of what I call attribute or functional information about those emissions. We just know they're emerging from boxes all around the planet at this hourly time step. But it was the first step to try to create a more granular, more detailed picture of what emissions look like. Excuse me. The next system we built is called Vulcan. And it was a project like FFS, now been around for probably 15 years. And it focuses on the United States and tries to go down to even more granular detail in both space and time. We go down to about a quarter square kilometer here, roughly speaking, every hour. But more important than that space and time is that Vulcan includes a lot of that functional information. And what I mean by functional information is not only the amount of the emissions, but whether it's from the on-road sector, is it a power plant? Is it a building? What type of building? It has that type of detail. And the policymaking community really has needed that kind of information because that's really how a lot of policies are designed. They're designed around a sector or a fuel or a piece of the landscape. And so we've been trying to build information that can satisfy that need. And so Vulcan's come a long way. It's only in the United States, but it's come a long way to try to deliver some of that information. Now, from Vulcan, we tried to then zoom even further down into the cityscape. Only done this in 5 urban areas in the United States. This happens to be the city of Indianapolis here, which was the first city that we attempted to do this for. And what you're seeing here is a mixture of buildings and roads. And here we're trying to go right down to the individual built structure scale. So we quantify emissions for every single building, every single road segment with 28 different vehicle classes, every hour, so on and so forth. The airport, the factories, rail lines, the entire, if there's any bit of CO2 emerging from this landscape from burning fossil fuel, we try to get it within this system. So these 3 different scales that I've talked about also are internally nested. And that's very important from a scientific point of view, and I think is very important from that accuracy trust metric that I mentioned that the financial markets really need, because we can conserve mass, which is a very important piece of science that you always try to strive for, because it lends accuracy to what you're doing. So we conserve mass at these various scales and nest each of these systems one within the other, almost like a Russian doll. It also has a standardized sort of approach across all these scales. It's consistent across the globe. Lots of attributes that you want in a reliable kind of information system. Now I'm going to show a couple applications of this information, or the way it could be used. We've tried to paint some of these out, sometimes in collaboration with individual cities to try to help them better understand their emitting landscape. But this is an example of one that we did in Los Angeles, where we were interested in intersecting low-income housing with rooftop solar potential. And again, by having detail right down to the building level, you can combine the emissions with income, with census data, with lots of other socioeconomic data to really start to dial out what policies might work and where. And of course, these days, greenhouse gases or greenhouse gas mitigation in cities is probably not going to be done in isolation of anything else. It's going to be done in concert with other interests and needs that a city has. And in this case, in Los Angeles, there was a lot of interest around solarization programs, but targeting low-income households. So we did a couple scenarios here where we cut off the income at $25,000, we cut it off at $50,000, just to show where within the city is best to focus to try to get the biggest return on both helping these consumers lower their energy costs, helping the city lower CO2, and stimulating more residential solar. And we created lots of statistics about what that means financially and in terms of greenhouse gas emissions. Another example we did in the city of Santa Monica, which happens to be the city that I grew up in. And here they were interested in these fossil fuel-free zones for the transportation sector, for the on-road sector, typically targeted at delivery vehicles, but we did some scenarios in which we did it for delivery trucks, we did it for all cars. And we just tried to show that if you block out certain segments of the city, how much CO2 do you get? How much is it relative to the city writ large or the neighborhood region, or, try to place that magnitude within context so they could see really what you're going to get by potentially going to the trouble of blocking out parts of the city. Of course, this has lots of other attributes. And that's another example of that. These things often aren't thought about in terms of greenhouse gases in isolation. But as probably we all know, especially after COVID, that you remove a lot of cars from the road and you have lots of other nice things occur. You lower local air pollution, it's quieter, wildlife returns in some cases. So this, again, is part of a larger decision-making matrix in a given city. So we're also moving on to trying lots of new things. And most importantly, a lot of the information I've shown you has been a bit US centric, because that's been the place that we've had the greatest facility to build this information, partly because the US and Western Europe, Japan, Canada, a lot of the high income industrial countries have an awful lot of data, and it's typically pretty transparent. But clearly other parts of the world need this granularity as well, but it's a lot harder to achieve because the data either isn't available, or if it is available, it's not transparent. You can't get at it. It's held in proprietary hands, or even by governments in some cases that just don't share it. So we're trying to pioneer going back to remote sensing again, but instead of using satellites to measure CO2 in the atmosphere, we're also using satellites to look at imagery, to actually characterize infrastructure at the surface, and thereby quantify emissions. And these are just some examples. Everybody's seen these now, of course. They're on the evening news, and lots of stories you see with all this wonderful, very high resolution commercial imagery. But one of its great powers, when you combine it with machine learning, is you can start to classify objects at the surface, the assets that are doing the emissions. We're even trying right now to count individual vehicles from space as a way to more accurately characterize on-road emissions in places in the world where we can't get the information in other ways. So lots of new science that combines both some of this new remote sensing with new machine learning type algorithms to tease out more and more information. And in some ways, a lot of this work right now in the last couple of years, myself and my colleagues that work in this area have been trying to present both to the US federal government and to government bodies around the world the idea that really what we probably should do, and what we're probably most efficient, is to build a system that's a lot like what we all know as the kind of weather forecast system. Everybody picks up their phone and gets, the next week's weather and the next hour and on a device. Underneath that, of course, is a massive system of modelers and scientists that sit in buildings all around the world running models and doing these weather forecasts. And it's a big system that grew over many years. We're arguing that greenhouse gas data should be done in much the same way. It should be built in the same sort of large and federated way to build a trusted foundation of data that then can be used by maybe private companies or weather apps or whomever to deliver that information to customers, be they a business, citizens, cities, state governments, federal governments, all the people that are interested in the data from this kind of core system. But it requires an awful lot to build it. We've established what we call prototypes of what this system might look like, but now we need to scale it up in significant ways. This is an ongoing conversation that we're trying to have. And in the last couple of years, there's been a lot of interest in actual progress and traction on starting to think about standing something like this up. I think we're in desperate need of it, and we're getting closer and closer every day. I'll mention one other thing that is coming out on Monday. This is a report that from the National Academy. I was on a committee writing this report. We've been doing it for the last few months. It's coming out on Monday. It's an attempt to both combine some of the things that I've just described with with really what decision makers need, and trying to really create that connection between all the advances in science and all the needs that various decision makers have up and down the decision-making chain. And I would argue that citizens are decision makers too. We all have lots of, or not, we have some power within our choices to alter our greenhouse gas emissions, not everything. So there's lots and lots of decision makers in this, and this report attempts to try to describe where we're at and what we can do next and connect up the science and the decision making. So if you're interested, I think there's a public release on Tuesday, I think this is, sorry, next week. Just sort of a bit of a coincidence with the talk tonight. And finally, a lot of the things that I've shown you have been put together by researchers in my own research group, in addition to colleagues elsewhere. And so I always have to thank all of them for the hard work that they do that makes a lot of this work look really great. And so both past members of my group, current members, and many of the funders, which have been multiple agencies in the US federal government that have made this work possible. So with that, I'll stop. Thanks everyone for patiently listening. And I think we should have plenty of time for questions and any discussion you'd like to have. So thanks.
Awesome. Thanks, Dr. Gurney. We don't have any questions yet, which is fine because I'm sure people are digesting. If you're not sure how the question system works here, just go ahead and navigate to the Q&A, drop your question in. If you can't do that, then send a message to us on the chat and we'll get that question to Dr. Gurney. In the meantime, we'll let you do that. We realize that we're dropping some links to things like the festival app that were only going to us and not you. So I'll go over a little bit of that again, just so folks can have that. And Aaron will put that in the link, the chat to everybody. So the first is just the festival website. This is where you can go to get information on basically everything about the festival, including what's coming up next. We have a brand new app that is new this year, available on Apple and Android. It's really streamlined a lot of this for especially users. That's been really important for folks to pull up their app and say, well, who's talking about what and when and where, and how can I register for it? And then finally, we're going to put up a survey link. I'll also, after the Q&A session is done, put up a slide for our sponsors, because of course, without our sponsors and donors, we couldn't do this for free and make sure this was free for everybody. So thank you for those of you who have attended tonight. We do have some questions here. Are you ready, Dr. Gurney?
I am.
All right. The first one asks, how does nuclear power add to carbon dioxide levels?
Yeah, it doesn't. This plot was just energy rather than emissions themselves. But out of this plot, nuclear and hydro do not emit CO2. They make energy, of course. But it is all these other fuels, natural gas, oil, and coal, of course, and biomass, that will emit CO2 into the atmosphere. Thanks for the question.
The next one, how do you envision individuals using emissions forecast data? So in terms of a family level or an individual level, these emissions forecast data, how can folks use those data to change their lifestyles or behaviors?
Yeah, I mean, I think one of the things that that many researchers have found, not just in this field, but in others, is something that's referred to as the dashboard effect, that that just by simply seeing the reality of emissions around you in a recognizable landscape actually begins to alter people's behavior. And probably a lot of people know this from if you've had a hybrid car, you know, or even most cars now will have, you know, a little dial that shows how efficiently you're driving. And that's an attempt, or it's one of the things that comes out of that is this idea of the dashboard effect, that actually that just having a visualization of your emissions starts to alter your behavior. You tend to be more conserving when you can see it. And because climate change has been so long a very abstract problem, I think, to the average person. It's been about global averages and or polar bears, and as much as we all care about polar bears, it's not something that's around us in an immediate way. So in some ways, a lot of the data and its visualization brings this problem directly into everybody's lives. If you can see as you're driving down the street, the emissions associated with the school you bring your kids to, and the coffee shop you go to, and the car you're driving, and have that all within a familiar context, it has a powerful influence on people's behavior. It also, I think, empowers people with, that next level, which is, I think, citizens, both, through their own behavior, of course, and everybody by this time is pretty familiar with, the ways that you conserve energy. But it also gives you information power to then lobby your city or your state or politicians. Data is often power. It gives people a lot of information and power to be convincing about doing something about the problem.
Thank you. The next question comes sort of methodology. How are you able to get granular greenhouse gas readings for individual buildings and roads and industrial plants for your models?
Yeah, thanks, Daryl. It might take a really long time to go through all that, but I'm going to use one example to give you at least a little feel for what we're doing, or maybe two. In the case of power plants, there actually is a lot of data directly from power plants. Many of them have in-stack monitors of the effluent. We'll use that, of course. Sometimes they'll have fuel accounts of the fuel going into a power plant, knowing a bit about the combustion process and the type of facility, we're able to estimate emissions. In the on-road sector, we use what's referred to as an activity-based approach. So we will use traffic counters that will count up volume of traffic. We don't measure it everywhere, of course, so you gap fill and you interpolate a lot of that data. We also have data on fleet distribution from county inspection and maintenance data. When we all bring our car in to register it or inspect it for emissions, that data we're able to get, anonymized, of course, but it gives us an idea of the fleet. So between the activity of vehicles on the road, knowing the type of fuels they're burning, knowing the vehicle distribution and the classes in various road segments, we're able to estimate the CO2 emissions. Because remember, CO2, when you have some information about the amount of energy that's going into a device, and if you know the type of combustion and the fuel, CO2 is a relatively easy thing to calculate, just because when we burn fossil fuel, we're effectively oxidizing almost all of the carbon in the fuel. Very, very little comes out in other forms, and that's intentional. To get the most amount of energy out of fossil fuel, you want to oxidize it to its highest oxidation state, which is CO2. And so often, just by either getting energy or some metric of activity, we're able to arrive at an estimate of CO2.
Awesome. Going down the line, Brandon asks, the new SEC proposed rule to require publicly traded companies to disclose GHG emissions also focuses on climate risk assessment. The question being, how could the data sets you talked about help both companies and cities better understand physical climate risk and energy transition risk?
Yeah, this is a good question, and I think it does go back to this the sort of financial aspect of the work. And by generating more accurate, consistent, methodologically consistent, and consistent data output over time, that is fundamentally one of the big components of risk. As I say, a lot of the potential investment in the mitigation space has really sat on the sidelines for an awfully long time. There's a lot of interest and a lot of potential investment that could come into the space, but there's just a lot of understandable worry about the risk. And I'll give you one example of risk just to flesh it out. With, for example, carbon offsets, where somebody will, a company may invest in saving a piece of tropical forest. It's a very important and useful thing to do. I think we all would like to see that. Problem is it's it's very hard to quantify the amount of CO2. It's very difficult to track it, so that if a piece of forest is destroyed or burned, sometimes it's very difficult to know, A, if it even happened, and B, how much. That gives rise to tremendous amounts of risk for serious investment, because serious investment, as I said, needs to know that what they're investing in is going to be realized in terms of the value they're after. And if it isn't, they're simply not going to invest. And I think that risk, that element of just pure, good, solid, trusted quantification is a big barrier and a big risk element for a lot of investors.
I'm gonna switch it up on you and pull from the bottom since I see the slides up. Is there a single source of CO2 responsible for the majority of climate warming? If so, what is it?
Yeah, I mean, the biggest part is electricity production. That remains the largest signal both globally and in most countries, not all, of course. There's many countries that, for example, Indonesia, their biosphere is actually their biggest source because of degradation of vegetation. But in the industrial countries that account for most of the emissions around the planet, electricity production remains the largest single definable signal.
Okay. Todd asks, what are some of the best mitigation industries within or close to cities? And what kinds of things should businesses and local governments do to bring carbon dioxide levels down?
Yeah, I mean, there are different governance levels have different purview or provenance or control over different parts of the emission problem. And using cities as an example, since it was brought up in this question, they can't control everything. They can't control people's individual choices and behavior in many cases. They can only control certain things. And an example of that would be, for example, building codes. Cities can do a lot around building codes, which require greater energy efficiency or different energy supply technologies. For example, there's a lot of movement towards more advanced heat pump systems in new buildings that are far, far more efficient, can supply both air conditioning and heating, and do so with a much lower energy penalty than older systems that are used. Cities can also enact transportation policies. They have a certain amount of control over roads. And often they can do that in concert with the federal government, since a lot of road money comes from the feds, but goes to local entities where they operationalize certain road projects. So that's just a couple of examples. And again, at every, states obviously have a different amount of control on certain things. Energy supply, for example, is difficult for a city to do much about. That typically needs to be done more at the state or even multi-state scale, because that's where the control over a lot of those systems is, and the federal scale, of course. So it depends on what scale, but hopefully a couple of examples in the city just flesh out what type of thing can be done.
Amy, I didn't miss you. Your question was, will you share a recording of this lecture? The answer is yes. It's actually available on the app, and you can go through the chat and download those depending on your device. It's also potentially up on YouTube by tomorrow. So we'll be posting these as they come. So just check your app and check YouTube, the Flagstaff channel, Flagstaff Festival of Science channel. And I think, Dr. Gurney, we have one more. This is from Bob. Since projection of emissions include the projection of necessary growing energy generation, can you characterize the sources of energy associated with your example of what are likely future emissions?
Yeah, that particular scenario still does have an awful lot of fossil fuel in it. And typically a lot of those high envelope projections will. The low projections are pretty substantial transitions to non-fossil based sources of energy. And while that may feel pessimistic, unfortunately, if the past is any guide, it does appear to be more likely than the high transition scenarios. Now, that's a judgment call. There's lots of stuff that goes into those scenarios, but I'll just give you an example. I mean, electric cars, which are a wonderful development, very exciting. If one can afford it, go out and buy an electric car. But they're still, in the US, only 2% of the fleet. Turning over the fleet is just hard. The numbers are just so daunting. The fossil fuel system is such a profound piece of the metabolism of this planet at this point, that it really is a pretty daunting task. Now that, as I say, I don't mean to sound pessimistic, because there's so much potential and so many exciting things occurring everywhere. Electric cars is just one example. Electrification in general has been quite profound, but there's lots of things going on all around the planet. Our struggle now, I think, is scaling it. And that is tough, because that means not only the investment I talked about, which I think is still, needs to be mobilized to a far, far greater degree. It also starts to intersect with, social norms and patterns of growth. And for example, some of these scenarios, all of them have projections of population, because clearly population is an element within all of these. Well, population is a difficult conversation to have. It reaches into social norms and other things. So there's a lot of things that go into them, but it does appear that, again, because of the size and persistence, and frankly, looking at the data over the last 20 years, when, if anything, what's happened is we have ridden the top of the projected scenarios over the last 20 years. That's sad, and I wish it were not the case, but that has been the case. That can change, but as a scientist, we have to look at just the raw probabilities and kind of be candid about that. And that does right now seem to be the most likely outcome. But I hope it changes, and I hope talks like this in very, very small ways start to do the little bits of change that needs to percolate everywhere on the planet.
Well, great. We hope so too, and we appreciate your time tonight. It was a great talk and some really good questions. So we appreciate everybody submitting those. If you wouldn't mind, Dr. Gurney, relinquishing the screen so I can pull up
You bet.
Our survey link, and give me a second to do that. Can everybody see this? Okay, so this is a QR code to our survey. You can also find it on scifest.org. Of course, we are very much interested in your opinions and how we can do better, what we did good, what we did not so good, and what you would like to see next year for the festival. Of course, there is an incentive, and you put your email in there, and you can get entered to win a pair of Apple AirPods. And finally, of course, again, to keep this completely free to everybody for the last 3+ decades, we want to thank our sponsors. We also want to thank our individual donors. All of this is also available on our app and our website. So again, thank you everyone for joining us. Thank you, Dr. Gurney, for your great talk tonight. And if y'all have any questions, you can always find us and contact us through the